Hello, we have here a resistor R connected to an AC power supply. The AC power supply has a sinusoidal voltage. Since R is connected directly to the AC power supply, the potential difference across the resistor, denoted by VR, has the same exact sinusoidal voltage. Now, what if we add a diode to the circuit here? Let's consider the occasions when the AC power supply is at its positive half cycles. So during the positive half cycles, this is the positive terminal and this is the negative terminal. So the AC power supply is trying to push current this way. So if you're trying to push a current through the diode this way, this diode is in forward bias. And when the diode is in forward bias, it behaves like a 0 ohm wire. So during the positive half cycles, it's as if the resistor is connected directly to the power supply. So the PD across the resistor will just copy the positive half cycle. Now let's consider the occasions when the AC power supply is at its negative half cycles. During negative half cycles, this is the negative terminal, this is the positive terminal. It's as if you have switched the battery around. So now the AC power supply is trying to push current this way. If you are trying to push current through a diode this way, you put the diode in reverse bias. When the diode is in reverse bias, it behaves like an open circuit. It puts up infinite resistance to the current flow, which means no current flows. If there's no current flowing through the resistor, the PD across it has got to be 0 because V is equal to IR and I is 0. So during the negative half cycles, we have 0 volt across the resistor. So the voltage across the resistor look like this. Hump, nothing, hum, nothing, hum, nothing. This is called half-wave rectification. Rectification because we have turned an alternating current into a direct current. Half-wave because, well, it looks like a half wave to you, right? So are you impressed with half-wave rectification? Not very, right? Because we have forfeited half the available power to us. In fact, I want you to think of the RMS value for the half-rectified voltage. You have learned that for AC voltage, if the peak voltage is V peak, then the RMS voltage is V peak divided by root 2. So can you figure out what is the RMS voltage for a half-wave rectified voltage? Pause the video to think of your answer. If not, I'm going to review the answer now. It's always easier to work with numbers. So let's say we're connecting a 3 volts DC across a 1 ohm resistor. Alright, so 3 volts DC across a 1 ohm resistor. In that case, the power is a constant 9 watt. 9 watts because V squared over R. So 3 squared divided by 1 ohm. So a constant 9 watts. So let me write down here. Power is constant 9 watts when the voltage is a 3 volt DC. Okay, so now let's consider a AC voltage with peak voltage of 3 volt. So we connect this voltage across the same 1 ohm resistor. This time round, the power will vary between 0 watt and 9 watt. So what is the average power? You look CC, you know it is 4.5 watts. So the average power is 4.5 watts. And its RMS value is V peak divided by root 2. You have learned this before. So now let's talk about the half-wave rectified voltage. So if you apply this half-wave rectified voltage to a 1 ohm resistor, then its power will vary between 0 and 9 during the positive half cycle, but the power is 0 during the negative half cycle. So what is the average power now? It's not 4.5 because 4.5 watts is the power when you have currents running during both the positive and the negative half cycles. But now you have currents running only during the positive half cycle. So what do you think? The average power over one period is now 2.25 watts, isn't it? The average power now is 2.25 watts because it's half of what you had before here, since you're running only half the time. So what is the root mean square voltage? So compared to this one, I have only 1/4 the power. So compared to this one, my RMS voltage should be half because power is equal to V squared over R, right? So if I halve my voltage, then my power becomes a quarter. Alternatively, you can think of it this way. So going from DC to AC, the power becomes halved, and that's why the RMS value is V peak divided by root 2. Then going from full AC to half AC, the power is halved one more time. So the RMS value has to be divided down by root 2 yet another time. So V peak divided by root 2 divided by root 2 gives you V peak divided by 2. Get it? Ta-ta!